So I'm Rick Rys. I'm an analyst at ARC. I have some experience with operator training simulators. I have a lot of process control experience. So I have spent a lot of time in high consequence processes. I've worked in oil refineries, chemical plants. I have a particular affinity for exothermic reactors. I don't mind the endothermic ones or even ionic reactors, like water stuff. So some of those things can cause a lot of damage. Um, so that's one of the reasons we named this operator training for high consequence processes. We know that in the nuclear industry, they have a standard ANSI 3.5 that requires them to build operator training simulators, and they have a very specific set of specifications for how accurate those training simulators must be. They are talking about all kinds of scenarios that must be built into the training program. Loss of instrument air, loss of steam pressure, on and on. And many of those simulations include all the way down to core meltdown. Before I get started, I wanted to bring two things up that I just noticed in some of the other sessions I attended. Our AV person down there, Preet, had a session there yesterday on uh, on augmented reality, virtual reality, extended reality, and she had a speaker there, Matt Malati from the Reliance Refinery. All right, and he was talking about how they were using some VR and AR stuff for operator training. We should have had him in the session here. We had Reliance speak from their refinery last year. Reliance Refinery, by the way, is the largest refinery in the world, 1,200 120,000 120,000 barrels per day. It's one hell of a 1,200,000 barrels per day of oil. That's roughly 10 times many refinery sizes. So it's a huge entity. And I was absolutely amazed when he mentioned that they have a 30% turnover per year. They are training new operators for 1 or 2 years of operation. All right. And he explained this particular situation where he had one time was involved with a CEO from Saudi Aramco and his CEO from Reliance, which by the way is privately held, all right, were in the same room. And so they were giving him a presentation on all these great training programs and mentioned also turnover. So the Saudi Aramco CEO mentioned to him, once you get these guys trained, can you send them our CVs? All right, we'd like to hire them. So, there's 30% turnover anyway. You can train them and we'll bring them. And also we know with a large refinery that way, they have a lot of infrastructure and can certainly build a very significant training simulation program, and they are amongst some of the most sophisticated training programs that we've seen. All right, can we? Which one? You can start it for me. All right. I'm going to give you one other place where simulation came into play. My previous session just next door, we had a session on drones for inspection and delivery. And talking to one of my speakers was a former pilot, and the other one's running a drone program with 50 people flying drones under his supervision. And it also became very clear that just to fly a drone, there are drone simulators. All right, so that means you have a stick and rudder, control panel with joysticks and a simulation, and the simulation specific to the specific drone you are flying. That is a very effective way to provide training to make sure you understand the drone. I had a drone once, and I really wish I had a simulator, because my worst fear of my drone was it's going to fly up and it's just going to keep going into the woods and it's going to be gone and I'm going to lose. A lot of people lost drones that way. Some of the newer ones have returned to home. All right. If they lose communication, it'll return to home. But in any event, the kind of the key theme from ARC best practices is that simulation is the most effective way to debug your control system, to train your operators, and has a wide range of other uses. I think those people that are the most sophisticated and comprehensive about getting the best return on investment from their simulators are using the know-how at the design part of the process, that they had the design tools with steady state flow sheet simulators, for example, that get converted to training simulators that are used for training maintenance, that are used by their engineering group, that are used by the control system designers that build the control strategies and want to test and evaluate whether a complex compressor surge control or a complex multivariable control on a crude unit or a cat cracker or something, when you build a sophisticated control and shutdown system, you want to make sure those things are going to work. So absolutely, in my experience, the best way of testing those control systems is to use a simulator, all right? And oh yeah, by the way, we can still use that simulator now for operator training at the same time, but there's engineering training involved as well. So anyway, one of the interesting things you might ask is, if you asked any one of these accidents, somebody at that plant the day before or that the accident happened, what's the likelihood of an accident happening in your facility? Oh, well, geez, it's not going to happen at my place. We have a good training program. We've got really good stuff. Everything's going to work right, right? But you ask them the day after, and they all kind of say, boy, operative training was one of the significant factors associated with the cause of this accident. You look at the post-accident analysis, and you find that very often operative training comes up as a root cause of that accident. And so I'm going to talk about 4 different accident situations. And I would also argue that if you look at the cost of some of these accidents and the liability that resulted and the insurance claims and all of the costs there, some of these accidents were really, really expensive. Some people suggest that Chernobyl cost of that accident was in the range of $500 billion. Fukushima accident, $200 billion. All right. Now, those things cause a lot of accidents because radiation got through a wide range of places. Technically, the nuclear plants, they don't really blow up. Chernobyl was a steam explosion. Fukushima was a meltdown. Yeah, the containment blew up, but it was a hydrogen explosion. So it's not a nuclear bomb. All right. And in the refining accidents, there's not quite as much energy available or quite as much damaging materials available, but you can certainly kill people and have accidents that have big, expensive consequences. Texas City was tens of billions of dollars, not hundreds of billions. The point I would make is that if you look at statistically, what are the odds of one of your processing units out here, whether you're a refinery or a chemical plant, or obviously a nuclear plant, is very, very significant. Those billions of dollars could buy a lot of training simulators. Those training simulators have significant influence if the training program is properly put together, that you could have reduced the likelihood of those accidents significantly. When you look at the accident after the fact. And I've been a very big champion here at ARC to try to encourage many of those refineries and chemical plants that do not use simulation to use it, to maintain it, to build it, and use it for multiple purposes. All right. The nuclear industry is forced to do that. They do that, and they do a really good job. In fact, the nuclear training simulators are typically a significant step up from the simulations you see in chemical, oil, and gas. So let's talk about some of these accidents. The Navy destroyer, SS John McCain, all right? They put this new control panel in there with the latest digital technology with a graphical user interface, all right? The problem was that they were navigating in close quarters, and it seemed like there was a lot of miscommunication, and ultimately ended up steering into another location. I should go back. And so basically this accident was very clearly tied to a lack of training and coordination. Now, there's multiple people that are required to navigate a ship, all right? So there's people that need to be sitting at this panel, there's people that are sitting at other locations in the ship, and all need to coordinate. And so in many cases, those training simulations, the training program needs to involve multiple parts of the organization. In a lot of the process plants, we have outside operators, inside operators, so field and console operators need to be trained. There's a similar type of situation on a ship. So this is a Chernobyl accident. When you work on the control systems, like I did in a lot of my career, you always want to see, well, what could go wrong, right? And their safety shutdown systems, of course, they were turned off here. They didn't think carefully at Chernobyl about what they were trying to do. What they were trying to do at Chernobyl was they wanted to, when the power plant shut down, they wanted to use the rotational inertia of the steam turbine to continue to generate electric power so that they could run the cooling pumps in the reactor. And they wanted to see that when they lost electric power, that those generators driven by the steam turbines would continue to make electric power for that minute or two before the diesel generators could start up. So they were actually thinking of this as an electrical system test. And so in order to run that test, they started to throttle down the reactor power during the day. And then for some reason they said, oh, no, we need your power. Put it back on. The grid needs that power. We don't want you to shut it down. Can you delay that test? So they delayed that test until the night shift. And there was a significant lack of coordination, a significant procedures not being followed. One of the problems you have in nuclear plants is when you shut them down, you can't start it up for 9 hours because of the xenon poisoning problem. The xenon that decomposing from iodine is picking up all the neutrons. It's absorbing neutrons so fast that you can't pull those rods out far enough to do that. So they start pulling the rods out. Let's make more neutrons. But those neutrons got sucked up by the xenon. But the xenon now life starts getting destroyed. Some of those neutrons are destroying xenon. And all of a sudden, the reactor ticks off and found an unstable situation. Suddenly, the power output for that reactor went skyrocket high. Some suggest it may have gone prompt critical. There's a little bit of controversy on that. But nevertheless, they didn't follow procedures. Clearly, had they tried to run a simulation of this entire event ahead of time, they would have uncovered some of these problems and probably learned the answer to the problem they were first trying to solve. So clearly, training and following procedures was a big problem here. The Texas City raffinate tower, all right? Here's an extended startup. The operators are trying to fill this raffinate tower up. It's got a steam reboiler on it. All right, they start to fill it up, and the level kind of goes a little bit high. So the level transmitter shows I think it's like 90% or something, but the level transmitter shows 90% even when it's 110, 120, 140, 400%, 500%, 1,000%. They filled up the entire distillation column with liquid, all right? And that liquid started to carry over the top of that. There's a great simulation here. If you search the Texas City explosion, there's a great simulation. I don't actually have it loaded here, but that show that they eventually filled up the entire tower that overflowed to a catch drum and suddenly started spraying liquid hydrocarbon out the top of a stack. That caught fire, had a pretty big explosion, killed a lot of people. Clearly, the operators didn't understand how the instrumentation worked, didn't have a good coordination between shifts again, and operator training could very well have saved this accident. You can't say for sure that it did. Then there's kind of this recent Boeing 737 MAX problem, right? Here, we lost a couple of aircraft there. Boeing is in huge trouble as a result of this. All of their whole fleet of 737s are grounded. But one of the interesting things is that they're internally within Boeing, one of the problems they had is they wanted to promote their 737 MAX as not requiring new pilot training. That would help reduce the cost, make it more competitive, all right? And so they specifically mentioned that, your training on earlier generation of 737 jets only needs a short computer course to brush up your skills, all right? But it turns out that this override, this safety shutdown system, by the way, we do have Shane talking about safety shutdown systems here because they're the things that are supposed to protect the operator after they mess up, all right? And hopefully the engineers don't disable those like Chernobyl, all right? But in any case, this override comes in, anti-stall activity, you're going to stall, and it starts throttling the angle of the plane down. Perhaps there's a sensor problem in some cases, but it became very hard for them to figure out how to disable that and take over control manually. They disabled it, take over control, it kicks in again, says, we're overriding, you're still going to stall, and they crashed. And if you look at the train of things here, you had individuals within a company arguing against spending the money to do training simulator to save money, and a lot of times the technical engineer's voice was crumbled that you really should have done. It wasn't listened to. So basically, sometimes it is a challenge to justify simulation. We've seen a lot of simulators put in my career where a brand new facility, I was working at the Sincor refinery in Venezuela. They built $4 or $5 million, built a whole training simulator for all process units in the refinery, had that up and running, trained the operators, and then evaporated. At the end of that product, that entire thing the training simulator machine got salvaged for spare parts. Nobody at the plant picked that up. They didn't have the infrastructure in the plant to think about the life cycle of that modeling and simulation effort that could have been used for design and continued to be used for maintenance and support and engineer training and control system testing. And so they didn't think of it in the life cycle cost, and that was one of the reasons why they were not able to keep it running, or didn't think important to keep running. They probably could have used that. All right. I don't know of any particular accidents at that site, although things like delayed cokers have a history of catching fire. They're a very dangerous unit. In any event, pilots, surgeon, heavy equipment operators, they are seeing simulation go. And with the modern advance of digital twins and digital emulation technology, the ability to build 3D spatial models much cheaper with LiDAR, the ability to have certainly computers that can run all the simulation. Virtually all the control system suppliers now that ARC is involved with offer a virtual simulation of their control system and HMI interface that can be connected to a process simulator. And so that's basically the exact configuration files for building the displays and for building the controls are loaded into a virtual machine. Engineering tends to be done with a virtual system rather than the actual real hardware on a checkout floor like we did in the old days. So in any event, there is a challenge to justify simulation, and it needs to be worked on in many organizations. And as I mentioned, ARC looks at that as a best practice for not just operator training, but for all of the multiple uses.